So now that we've you know, looked at curve sketching and sort of used local extrema among other tools to look at that, um, I want to take another look at how we can understand this concept of extrema, right? Um, let's say you have some function that you want to maximize, right? Maybe it's fuel economy, right? A lot of times I've drawn fuel economy like this, but things are a little bit more complicated than that. Maybe you drive something like a stick shift, right? So you have a little bit more control versus something like a continuously variable transmission, right? In that case, your fuel economy might look a little bit something like this, okay? And all of a sudden, this is really interesting because if you're just looking for local extrema, right, the tools that we've built will peg this, this, and this all the same, right? It'll call it, hey, these are all local extrema. They're all bigger than the stuff around it. And it's like, well, yes, that's true, but if I'm trying to, maximize fuel economy, I want to know this, not this, right? Um, we're not looking for uh, the biggest in an area. We're looking at the biggest, ever, right? For all of the values in the domain, what is my biggest value or my smallest value, right? Um, and this, inspires us to write the following definition, right? So let's say if f of x is less than or equal to f of c for all x in the domain of f, right? So if um, any value of x is less than or equal to some value f of c, well then f of c is called the absolute maximum of our function f, right? This directly contrasts with local maximum as we had defined it before. And then of course there's the carbon copy definition. If I flip my sign, right, if f of x is greater than or equal to f of c for everything in our domain, well, then that would make f of c our absolute minimum, okay? And we can, throw up a handful of graphs, to sort of run over, some of the basic situations. We can grab a handful of sets of axes. Let's see if I can draw something symmetrical first try. Nope, but it will work. It's always fun trying to eyeball having the same, I guess, size on everything, but that will work. It's close enough. Let's throw down a couple of graphs, right? We can have something like y equals x squared, which is going to look, well, it's not a great parabola. Let's see if we can do a little bit better. Sure, right? This thing is going to have an absolute minimum right here, and it's not going to have an absolute maximum, right? It's going to go arbitrarily large. As x gets arbitrarily large, y is going to get arbitrarily large as well, right? So there is no absolute maximum. Conversely, maybe we look at something like y is 4 minus x squared. That's going to give us something like this. If I were to take it over just a bit, maybe like that, right? This one has an absolute maximum right there at y equals 4, but it doesn't have an absolute minimum because it's going to get arbitrarily negative. Okay, well, what about something, this is just a fun example. X times 1 minus x squared. You could go through, using the tools that we developed in the last part to graph this, but it's going to look something like this. Its domain is only, between -1 and 1, right? Everything out here is not defined because of our square root. And so because of that, well, look at this. We have a maximum and we have a minimum, right? This one achieves both an absolute maximum and an absolute minimum. But then if we look at something like y equals x cubed, it's going to go like this. This doesn't have an absolute maximum or an absolute minimum. Neither, it just doesn't have either. Since it doesn't have either, you can't, really do anything with that if you're looking for these absolute extrema. And one thing that I want you to notice is that the thing that stops these from either having one or both of the extrema is that in this instance, they're going to continue arbitrarily far either way. And because of the way that our function works, even though it's continuous, it's zooming off to infinity, right? But something like this, with a domain that isn't, infinite, it achieves both of them. And the theorem that I'm about to, walk you through here and then, state formally on the next page, we're not going to prove it. But it should sort of, make sense that, what happens if I take any of these functions and I chop its domain up? Say, hey, we're only looking at this function between those green lines. Well, since it's continuous, as long as I include those endpoints, it's going to have an absolute maximum and an absolute minimum, right? And we can put those green lines anywhere we want. The moment we're looking at a continuous function on a closed interval, it's going to obtain both its absolute maximum and its absolute minimum, right? It's not like, any of these unrestricted cases where things can just blow up to infinity because our function is continuous. Okay, so let's sort of write that down as a theorem. So if the function, a function, f is continuous on AB, then f has both an absolute max value and an absolute minimum value on that interval AB. Okay. And this seems very, very powerful. And we can actually take it one step further. Let's first restrict to just worrying about absolute maximum, right? There are two possible cases. Either the function attains its absolute maximum on the boundary, right, either at A or B, or somewhere in the middle, right? Let's take a look back at we can take a look back at slicing off various portions of this guy, right? Either, I guess I'll move that so that it's centered, right? If we were to say choose this portion, right, and we're looking for the absolute max, right, it happens here at the local extrema. right? But if we were to say choose this interval, it happens at the edge, right here. So that's going to sort of that points us to this idea that either it's going to happen somewhere in the middle, or it's going to happen on one of the edges, right? Because it has to happen somewhere. But notice, if it happens somewhere in the middle, it has to be at one of our relative extremas, right? One of our local maximums. And if it doesn't happen at one of these local extremas, then it's got to happen at the endpoints, which gives us a pretty slick way to look at this. All right, let's say we have a function that looks maybe like this. You know, it's going to start like this. It's going to go down, kind of come to a point, then it's going to go, oh, I didn't know it did that. That's nice. It's going to go down further and then up. Okay. Let's say we have a function that looks like that. Well, if we start to label points, we have a local minimum right here. We have a local maximum. We have an absolute minimum here, also one of our local minimums. And then we have an absolute maximum here. Notice our absolute minimum happens at one of our local extrema, and our absolute maximum happens on our boundary, right? Those are the two possible cases. Okay. And the way that we could find this, right, is, well, what if we took the derivative, right, and found the values for these 3 points, right? You know, maybe call them x1, x2, and x3. A and B are our endpoints. And if we were to just collect the boundary points and the local extrema, well, then those are the only places where our absolute minimum or maximum could occur. We can just calculate f of those values, and we're done, right? Let's you know, grab a you know, specific example to work through this, right? Let's say find the extrema, the absolute extrema in this case, and we'll say f of x equals x squared. And we'll say it's defined on, say, -1 to 2. Okay. And, you know, what's really nice is where, you know, this function is continuous and differentiable on this whole interval, right? Because it's a polynomial, so it's continuous and differentiable everywhere. And so we can take a derivative, right? F prime of x is 2x. And so then we only have one critical number, right? So we need to write down our critical number. Well, it's just x equals 0. So that means we have the following test points. Right? We need to check the boundaries, x equals -1. We need to test the critical points in the middle, and we need to test the other boundary point. Okay? And so let's run through these, right? We have little f of -1. -1 squared is 1. F of 0 is 0. And f of 2 is 4. So that tells us that my absolute minimum is f of 0 equals 0, and my absolute maximum is f of 2 equals 4. And if you were to quickly jot down a graph of this, right, you would see that this function looks something like that, right? With our domain restriction, or, again, I guess this guy needs to get moved over a little bit. So this is what our function would look like, and checking with our eyeballs, that is the absolute maximum, and that is the absolute minimum. But let's look at something that's a bit more involved than x squared, right? Let's say find the absolute extrema. What function should we do? Let's say, let's grab a cubic. X squared, or x cubed, minus 2x squared, minus 4x plus 4x. And then let's do this on 0, 3. Well, once again, we're continuous and differentiable because it's a polynomial. We're all good there. And so we need to take our derivative. Well, our derivative is 3x squared minus 4x minus 4. And we can factor this, factors it looks like into 3x plus 2 and x minus 2, okay? And that's going to give us 2 critical points, right? And then this is equal to 0 when x is negative 2/3 and x equals 2. But notice, negative 2/3 is not in the domain that we're interested in, right? We're only interested in the, interval from 0 to 3. And since this is outside, we can chuck it in the garbage and not worry about it, okay? And then from here, once again, we can write down our test points. It's a T, not an F, test points. And well, we have the boundary, which is x equals 0. We have our interior point, the local extrema, which is x equals 2, and then we have 3. And we can test the values. F of 0 is just going to be the constant term, which is 4. F of 2, that looks like it's going to be 2 cubed, or 8, minus 2 cubed, or 8, minus 8 plus 4, which is going to come out to negative 4. And then f of 3, 3 cubed, minus 2 times 3 squared, minus 12 plus 4. So it looks like we're going to have 27 minus 18 minus 12, so minus 30, plus 4 for 1, okay? And now with this information, we can conclude, right, just by comparing all of the possible candidates that could be our absolute minimum or maximum, and picking the biggest one for the absolute max, right, which is f of 0 equals 4, and then picking the least one for an absolute minimum of f of 2 equals negative 4. For the next one, let's complicate it a little bit. Let's take a look at the absolute extrema. I guess 4. Let's say something like x to the 2/3 on, and let's do a larger interval, say negative 1 to 8. And this gets a little bit more complicated because if we take a look at our derivative, we're going to get 2/3 x to the 2/3 minus 1, or minus 1/3, right? So 2 over 3 x to the 1/3. And this is a little bit more complicated because our function is not differentiable at x equals 0. But even though it's not differentiable there, right? Our derivative does not exist. It's still going to give us a critical point because our function is defined there, right? Notice that our function is continuous on this interval. Okay, so what that then tells us is that this is going to give us one critical point, right? We need to check x equals 0. It's our only critical number, so we get our set of test points, right? We have the boundary, 0, and the other boundary, and we start checking them. So -1, -1 squared is 1, and then you take the cube root of it, and you get 1. F of 0 is, well, 0. And then f of 8, well, I could square it and then take the cube root, or I could take the cube root and get 2, and then square it to get 4. And then from here, once again, it's very easy to read off our absolute minimum is f of 0 equals 0, and our absolute maximum is f of 8 equals 4. And this is useful for situations outside of the realm of theory. You might be interested in what level of production yields the maximum profit, right? You're not concerned with local extrema there. You want the highest possible profit, right? A farmer, right, might be able to find some relationship between amount of fertilizer used and like crop yield, right? Well, then obviously you want to maximize that, right? These problems are known as optimization problems, right? You're trying to optimize some quantity. Okay. Here's one sort of stranger example with this, and then we'll look at a cost function next, or rather an average cost function. When you cough, right, your trachea contracts, right, and that allows the airflow through it to increase, right? It goes faster, right? That situation is modeled by this, right? So the velocity coming out, right? The velocity of the cough is a function of our radius. So it's some constant k. It's some positive constant k that's dependent on the length. Little r squared times big R minus r, right? Where our little r is the contracted radius, which is the variable that we're actually writing this as a function of. And then here's our normal radius, right? So it might actually be helpful to write v as a function of our radius. Okay. And then say you're trying to maximize this, velocity, say, you're trying to model how the body would best approach, maybe you're choking on something and you want to maximize the velocity of that air in order to try and dislodge, whatever that object is. And then all of a sudden, this is an optimization problem, right? And we can look for what's going on, right? We can first sort of think through our domain. Well, the smallest that r could get would be 0, right? If it contracted all the way to 0, it wouldn't quite make all that much sense, right? But that's as small as it could go. And the biggest it could ever get is the normal radius, right? Not contracting at all. And so now we're trying to optimize V of R on this. And we can, march through the same steps. Now we're just using symbols instead of numbers. We can take our derivative, right? V prime, and then, as long as we remember that K and R are constants, we can march through this like normal, right? This is the product rule. So we can do the derivative of the first, 2kr times r minus r, plus kr squared. The derivative of this guy, big R, is a constant, so that goes away. The derivative of minus little r is just a -1. And then if we distribute this, right, we're going to see 2kr big R minus 2kr squared minus kr squared. And then if we factor out a kr out of everything, we're going to see that this comes out to kr times minus 3r plus 2 big R. So then this is our derivative. And following what we did before, we're looking for where this equals 0. And so if we were to set kr times minus 3r plus 2 big R equals 0, well then either this equals 0 or this equals 0. If this were to equal 0, we would just get R equals 0. But if this were to equal 0, we could subtract this over to the other side, divide by 3, and we would get that R is 2 big R over 3. So those are our two critical points. But now notice, as we go to collect our test points, right, we need either side of our domain. So R equals 0. We now don't need to add this anymore because it's already one of our endpoints. 2R over 3 and R, right? And let's see what happens when we plug these in, right? What happens if we put 0 into our function? Well, if we put 0 into our function, the whole thing is going to collapse to 0, right? Because we have a factor of 0. So we get 0. What happens if we put R, just sort of testing the endpoints? Well, if we put little r equals big R, well, then this factor is 0, and our whole thing collapses. If we put V is 2R over 3, I'll let you sort of run through the math on this. It ends up being, a handful of algebra to simplify this, but it's not difficult. It may be a bit tedious. This comes out to 4k over 27 r cubed, okay? But r is positive and k is positive. So this is my absolute maximum. So then this is going to tell us if we're looking to maximize the velocity, well then the trachea should contract to 2/3 of its normal radius, okay? And then for our next example, let's take a look at something utilizing one of our average cost functions, right? Let's say it's given by 0.30 x squared, 0.08x plus 40 may have, there you go, where our domain is x greater than 0, okay? No one ended up sending any emails with, various commodity ideas, so let's, just go back to chess sets again. we have this average cost function, the cost of manufacturing X chess sets. Okay. And then we want to actually show that 500 units per day gives the minimum average cost. And so, as a statement, this seems a little bit different than what we've been doing before, but we can kind of walk through it in a similar idea, right? The first thing that we want to do is take a derivative, right? That's how we're going to optimize. And as we take our derivative, this 2 is going to drop down and then become a 1. So we'll get 0.002x. The x on minus 0.08 becomes a 1. My 40 drops, and then for the last term, the 500 is going to stay the same. The x to the negative 1 becomes x to the negative 2, and then the negative 1 is going to drop down, okay? So our first step here, right, is actually going to be showing that c bar prime of 500 equals 0, right? Because that will mean that it's a local extrema, right? That's sort of our first step. Since it's on, the interior of our domain here. And believe it or not, if you go to your favorite calculator, plug this in, would you look at that? It equals 0, almost like 500 was selected on purpose. So we know that it's a critical number. How do we know that it's a minimum, right? Well, we can actually use the second derivative test here, right? C bar double prime, right? It's going to be 0.002. The minus 0.08 goes away. And then now it's going to be plus, and then this negative 2 is going to drop down, and we're going to get plus 10,000 over x cubed. And here's what I want you to notice, right? When you plug in 500 into this, you're going to get a number, clearly. We don't, thankfully, need to calculate 500 cubed or, dividing 10,000 by that. All we need to do is notice that this is greater than 0, right? There's no way for this to be less than 0. And so that means that our function is concave up there. So x equals 500 is a local minimum. Okay. But we can actually go a little bit further than this, right? Because notice this, right? On our domain where x is strictly positive, this function is always positive, which means our function is always concave up, which means there's never a time where it can have another local extrema or where it could possibly get lower, right? Because for it to get lower, it would need to start to decrease again. And so what that means, we can write this down, right? So since my second derivative of our average cost function is greater than 0 for all x greater than 0, right? Then my average cost function is concave up everywhere. So that it immediately gives us that c bar of 500 is the absolute minimum. Okay, and we could calculate that, right? C bar of 500. I'll let you again work this out on your own. You can, um, plug this into your calculator, work it out by hand. Comes out to 35. So the most efficient way to run your chess manufacturing thing is to produce 500 units a day, at which point they will cost $35 a piece. And if you produce any more or any less, your average cost will go up. Okay. That's going to do it for this set of lectures. We have one more lecture in chapter 4. I know I said right at the beginning of last week that we were going to try and finish up chapter 4 this week. There's a little bit more optimization to do. We'll knock that out right at the start of next week. So I hope you have a great weekend.